Suppose you have a company and you want to know what is the maximum profit and what is the minimum loss that you can have for your company. That's where we talk about two important topics, local extrema and absolute minimum and absolute maximum. For the local extrema, we can define something that we call local minimum. We say that a function has a local minimum at a value like c if the output value of the function at that value, so this is the output value, is minimum value of function on some interval. At the same time, we can define local maximum, or basically in a month, what is the maximum profit, for example. At x equals to c, the function takes its local maximum if f of c, the output value of the function, is the maximum value of f. We can also define extreme values on an interval. An absolute minimum of function f of x is f of a, where f of a is the smallest output value in that interval. The absolute maximum of function f is f of a, or the output value of the function, which is maximum with respect to all other output values. So basically, suppose you have a company and you want to know, since you started the company, what is the maximum profit? You can find some local maximum profit in different months, and then between all of those local maximum profits, you take the one that is highest. Let's take a look at this visualization together. Here on the horizontal line, we have x equals to a, x equals to c, x equals to e, x equals to d, and x equals to b. Take a look at your output values. When x is equal to a, you have f of a. When x is equal to c, you have f of c. When x is equal to e, you have f of e. These are all are output values of the function. When x is equal to d, you have f of d. When x is equal to b, you have the output value as f of b. Very good. So let us compare these output values. Between all of these output values, f of a is the absolute minimum. There is no smaller value for function f than when x is equal to a. Let's take a look at f of c. F of c and f of d are comparable. This guy is a local maximum. At the same time, f of d is a local maximum, but between f of c and f of d is the highest. Between f of c and f of d is the highest. That's why we say that it is absolute maximum. Well, f of e is another local minimum, but remember that f of a is the smallest of all. Local minimum at b. F of b is also a minimum value for the function and is a local. What is the definition of critical point? A number like c. This number is on the horizontal line. In the domain of function f is called a critical point if, when you take the derivative of the function at that value is equal to 0, or the derivative doesn't exist. So these are two criteria that basically gives us the critical point or critical points of a function. Let us start with a very simple function. F of x is 1 plus 2x. So if I take the derivative of this function, f prime of x is 0 plus 2 times 1, or it is 2. So it seems like this function derivative is a positive value right? 2 is not. 0 and 2 indeed exist. So let us sketch the graph of this function. And the question says, hey, the domain is all values more than or equals to -1. So let us take a look at the graph together. If I visualize this line, then x is equal to -1, x and f of x, then x is equal to -1. My function is 1 minus 2, which is -1. So at -1, we have -1, this point. When x is equal to 0, it becomes 1 plus 0 or 1, 0 and 1. When x is equal to 1, for example, you get 1 plus 2 or 3. So at 1, we have a 3, 2, and 3. So here we go. So let's connect these dots together to have the graph of the function, and it starts from this value, this point, and the rest of the numbers are not included. So take a look. Here I have my function starting at this point. So it seems like when x is equal to -1, my f of -1 is equal to -1. So this is the lowest point, lowest value, smallest value of the function, right? So do we see any maximum? We don't have any maximum. The function continues going up. There is no maximum. So we say that the function has a minimum at -1, which is f of -1 or -1. This is this value. So for example, if it was your loss function, the minimum loss value is -1. Let's take a look at another function. Here we have a quadratic function, 1 minus x squared. Let's take the derivative of this function. F prime of x is equal to 0 minus 2x. So f prime of x is equal to minus 2x. Set f prime of x to equal to 0 to find the critical value. So minus 2x is equal to 0. It means that x must be 0. So when x is equal to 0, f of 0 is 1 minus 0 squared or 1. So let's see if this point is a minimum point or is a maximum point. Let's graph this. Let's visualize this. Here I have the following case. When x is bounded between 0 and 1, look at some portion of the graph. So when x is equal to 0, I get 1 back. But I'm going to put a hole here because 0 is not included. So what if my x is equal to 1? When x is equal to 1, I get 0 back. At 1, I'm going to have a 0. But again, I'm going to use a hole because 1 is not included in the domain. If you were to plug in, for example, -1, you could see that, hey, at -1, the graph becomes 0 as well. So this is just for the sake of helping you to visualize this function. The rest of the function that is between 0 and 1 is on the far right side. So we don't need this portion actually. We'll just use this dots to help us visualize the function. Well, at x equals to 0, you have a maximum, and at x equals to 1, you have a minimum. So you're going to write it this way. At x equal to 0, we have a maximum, which is f of 0, and f of 0, as you know, is equal to 1. At x equals to 1, we have a minimum, which is f of 1 or 0. Let's take a look at another function. We want to find the critical numbers of the following function. To find the critical points, we take the derivative of the function. F prime of x is equal to 2 minus 6 times x. Set f prime of x equal to 0, 2 minus 6 times x is equal to 0, or 6 times x is equal to 2, or x is 2 divided by 6, or a third. Let's take a look at our Desmos. We are interested in seeing how we can visualize this function. Let me share the screen with you guys. So here we have 2x minus 3x squared. This is your function. So as you can see, it only has one maximum. There is no minimum for this function. You can scroll and see there is no minimum to this function. So at x equals to a third, the value that we just found algebraically, we expect to see a maximum for this function. So let us go back here. We only have one critical value, x equals to a third. At this value, the output of the function is f of a third, which is equal to, now I'm looking at my function again, 2 times a third minus 3 times a third to power 2. It's equal to 2 divided by 3 minus 3 over 9, or a third, or 2 minus 1 divided by 3, or 1 over 3. So in this special case, your x is a third, your y is also a third. And if someone asks you what is the local minimum, local maximum of the function, we're going to say that we only have a local maximum that happens to be our absolute maximum as well. So this is the maximum of the function. Let's take a look at another example for you. We have another quadratic function, x squared minus 2x plus 2. Let's take a look at Desmos and see what the function looks like. So here I have x squared minus 2x plus 2. This is my function. So as you can see, by visualization, I expect to see one critical value, which is resulting in the minimum of the function. So let us go back to our note and do the algebra. So to find the critical values, you find the derivative of the function. So f prime of x is equal to 2x minus 2. Set f prime of x equal to 0 and solve for x. 2x minus 2 is equal to 0. 2x is equal to 2. Well, x becomes 2 over 2 or 1. So at x equals to 2, at x equals to, 1, we have a minimum, which is f of 1. But I'm using this function, right? Here we go. And 1 belongs to the domain, so we don't have any issue. You're going to have 1 squared minus 2 times 1 plus 2 or 1 minus 2 plus 2, these two get cancelled out, you get 1 back. So the minimum value of the function is 1. The minimum of the function is 1. What about the maximum of the function? Remember that we look at this function when x is bounded between 0 and 3. If you were to graph this function, when x is equal to 0, x and y, when x is equal to 0, we have 0 squared minus 2 times 0 plus 2, which is 2. So at 0, we have a 2. When x is equal to 1, we saw that the function is 1. At 1, we have a 1. What if x is equal to 3? When x is equal to 3, you have 3 squared minus 2 times 3 plus 2, or you have 9 minus 6 plus 2, or you have 3 plus 2, which is 5. So basically, when x is equal to 2, you have 1, 2, 3, 4, 5. So let's just have the graph here. So basically, this is the behavior of this function and this interval between 0 and 3. You could shift this a little bit to make it more nicer. So let me just move this point a little bit here. This is 1. Let's put 3 here to make it a little bit visible for students. 0, 3, and you have a 5. This is basically the portion of the graph that we are visualizing. So this is going to be your minimum, and this point is your maximum. That's how we analyze different types of functions, finding their minimum and maximum. We find the derivative of the function, set it equal to 0 to find the critical value. Then if we have a specific interval, we need to plug in those values into the function to find the output values as well. Then we're going to compare the output values. For example, here I compared 2 and 5. So of course 5 is more than 2. So it means that you have maximum at 5.